All right, there we go. So today we're going to be talking about continuous deployment with Akka.Cluster and Kubernetes. My name is Aaron Standard. I'm the founder and CEO of Petabridge, and I'm one of the co-founders of the Akka.NET project. In terms of what I do day to day on the Akka.NET project, I'm the release manager for the project, and I'm also responsible for Akka.Cluster and Akka.Remote. So our sort of low-level networking systems is what I tend to spend most of my time on. Now, in terms of what we're going to cover today, we're going to give a very brief overview of Akka.Cluster and how it works. I'm assuming that most of the people on this call have had at least some exposure to it. If you haven't, we have some other YouTube videos and blog posts and training courses on that. So we're not going to go into a huge amount of detail, just enough to kind of be literate with what we're going to cover today. We're going to cover some Docker and .NET Core fundamentals. Now, I'm going to assume the folks on this call are a little bit less familiar with Docker. So we'll go ahead and cover that in a little bit more detail. We're going to talk about some best practices for using Docker and Akka.Cluster together. So specifically, we're going to talk about how to take care of things like bootstrapping, making sure that whenever you spin up a new Docker container, all the Akka.Cluster nodes are able to select the correct IP address and port. That way they can all connect to each other when they're starting up. And then we're going to cover some Kubernetes concepts. So we're going to talk about how to use Kubernetes to go and orchestrate a full-blown Akka.NET cluster. We're going to talk about the Azure Kubernetes service real briefly. We're going to be using that for our little demo today. And then we're going to talk about how to combine all these concepts together in order to continuously deliver or continuously deploy whatever your kind of preferred terminology is. We're going to go ahead and show you how to combine all these together in order to carry out continuous deployment. Now, I should point out, this isn't going to be sort of a step-by-step, every single little nitpicking detail that you need to accomplish all of these. I'm going to kind of outline the general process for doing it. Petabridge is actually doing a training tour, and we've announced 2 different locations for it. It's a 2-day-long workshop, but we're going to actually do the step-by-step, point-by-point sort of delivery of everything that I'm going to be covering today. So if you're interested in getting some real hands-on experience and training doing that, I'm going to have a link towards the end of the talk today where you can register for our Houston or our Amsterdam training locations for that. So I'll go ahead and bring that up at the very end today. All right. Now, the first question I have, and I'm going to send out a poll real quickly, is is anyone currently using .NET Core, or are they planning on using it? So I went ahead and just sent that poll out there, and I'll collect the results. But while that's going out, I'm going to go ahead and explain why we're going to use .NET Core for delivering an Akka.NET application. So we're going to use .NET Core because it's cross-platform. It's extremely fast. So I just read this morning that the performance of ASP.NET Core 3.0 is 45% faster than ASP.NET Core 2.2. So .NET Core is getting a whole bunch of performance tuning all the time. That's increasingly becoming a really important sort of focal point for a lot of Akka.NET users. It's lightweight, so it's much easier to distribute .NET Core applications than .NET Framework ones. But really the biggest reasons why we're going to focus on .NET Core is this is kind of the direction the platform is moving in. Microsoft and the other sort of big .NET open source projects that are part of the .NET Foundation are really trying to drive their users towards sort of consolidating around .NET Core because it's a bit more flexible. We're able to iterate faster and introduce new APIs and do all these new things. Now the .NET Framework's not going to go away. There's some functionality that'll never make it into .NET Core. But for the sake of this course today, the biggest reason we're going to look at .NET Core is because it plays really well with Docker. The .NET Framework is much harder to distribute. It only works on Windows containers. It doesn't give us the ability to run on sort of lightweight Linux containers, which is what we're going to be using today. All right, so according to the poll, about 90% of attendees voted. 76% of respondents said, yes, we are already using .NET Core. 22% said no, but we want to use it. And then 2% said we haven't looked into it yet. So already there's a lot of mind share among the people who are attending today in trying to take advantage of .NET Core. Now, the next poll question I'm going to open up is, have you ever used Docker before? I'm going to go ahead and launch that now. So while that's running, so why Docker? Well, Docker is fairly ubiquitous. Every major open source project usually has some way of distributing, some part of their infrastructure as Docker containers. So if you want to play with Redis or MySQL or Cassandra or Zipkin or Jaeger and all sorts of other tracing, monitoring, and database tools, Docker is a pretty easy way to go ahead and get your arms wrapped around that. And on top of that, Docker enjoys native support in Linux, OS X, Windows, you name it. So it's a fairly ubiquitous tool. It's kind of being used everywhere. But the big reasons why I really like Docker is the fact that you have a really easily reproducible configuration format, the Dockerfile, used for going and compiling and creating the Docker images that your application runs inside of. On top of that, these Docker files are composable. You can go ahead and inherit from a base image and extend it with your own modifications. So for instance, if you want to take the .NET Core base image and use that to run your own application, all you have to do is just copy your binary files from a .NET publish operation into the Docker container and you're good to go. So that makes it really easy to go ahead and leverage some of the work that companies like Microsoft or Oracle or some of the other really big sort of open source platform companies drive. But I think the biggest reason why I really like Docker and why I think it's going to increasingly be a popular choice for both startup companies and big enterprises is the fact that it's really easy to share the output of a Docker build via these compiled Docker images. We go and upload these images to a Docker repository, and they're just about as easy to share as NuGet packages. So that's much simpler than what we had before, which is using things like trying to share VM images, or maybe if you were a little bit more sophisticated, you might have used Chef or Ansible or something to dynamically reproduce those. Docker is way easier by comparison. And I say that as someone who used Ansible and other tools fairly heavily in the past. Okay. So in terms of our poll respondents, 38% said yes, we're using Docker in production. 30% said yes, but just as a proof of concept. 18% said yes, just for fun, and 14% said no, never. So we have a good range of different types of people attending today. Now next, why Kubernetes? So Kubernetes, and actually I've got another poll question for this. Have you ever used Kubernetes before? I'm gonna go ahead and launch that. All right, so why Kubernetes? Well, first, Kubernetes is ubiquitous. It runs on premise, runs in the cloud, etc. So Kubernetes is becoming kind of an interesting technology choice because, in terms of my experience here at Petabridge, we do consulting and training and support with a lot of different companies that are building, enterprise applications that do everything from, medical device, IoT type stuff to startups that are, selling e-commerce products to big logistics and travel companies to big finance companies that are doing things like high frequency trading. We've seen Kubernetes appear in like all of these different environments, even including, big Fortune 500 companies here in the United States. And the reason why is because you can get Kubernetes up and running in your own data center using a turnkey solution like Rancher Labs, or you can get a really easily hosted version of it up and running on the cloud using something like Azure Kubernetes Service, which we're going to look at in a moment. The other reasons why Kubernetes is a good choice for Akka.Cluster, in my opinion, is that it has really robust deployment models. Specifically, it has the ability to handle deployment of stateful applications, which is this kind of gap that most deployment tools don't really address very well. So if you've used something like Octopus Deploy or some other sort of delivery solutions, the model those applications tend to assume for how your software should be deployed is they assume your applications are stateless web applications running under a load balancer, and that all of your application state is parked in a database somewhere. Well, as we all know, if we've worked with Akka.Cluster, stateful applications don't behave that way. Their in-memory application state is something that they have to manage very carefully in order to make sure we comply with all of our businesses, consistency and availability requirements. Kubernetes has really good built-in tools that make that process easy to work with. So that's something that we're going to be leveraging today. And then finally, the last big reason for Kubernetes is that it has a really rich ecosystem. There's lots of open source and proprietary tooling built on top of it that make it a pretty good choice for working inside of an enterprise environment. Okay. Now, in terms of our poll results here, 54% of respondents said nope, never looked at Kubernetes. 13% said yes, just for fun. 16% said yes for proof of concept. Then 18% said yes, we are using it in production. So it looks like most of the folks who are attending today have not had a chance to use Kubernetes yet. And by the way, in terms of questions, I'll take those at the very end today. Now, why Azure Kubernetes Service? Why are we going to be using this? Honestly, we're going to use it because it only takes a few minutes to set up. So it's a fairly easy sort of way to try to get your feet wet with Kubernetes. It integrates really well with Azure DevOps, which we're going to be using for actually running our build pipelines today. And more or less, it's just a really great environment for learning Kubernetes. So that's what we're going to go ahead and start with today. Now, I'm going to go ahead and show you the end-to-end sort of delivery process here for Akka.Cluster continuous deployment. What we're going to do is every single time we want to do a deployment, we basically merge, and by the way, I'm going to do this in a public GitHub repository, and I'm going to show you a little demo of this at the very beginning here. We push our latest changes into the master branch on GitHub. Then we're going to tag a release. So we're going to use Git tagging, which is a feature that, whenever you're working with GitHub, if you want to say this is version 1.0 of our software, you apply a tag to that, you push that up to the repo, and that basically lets everyone know, here's the point in time where the software was when version 1.0 rolled out. And using Azure pipelines, what we're going to do is every time a Git tag gets added to our repository, this is going to trigger the creation of some new Docker images via Azure pipelines. So it's going to use a build script that I wrote. And by the way, this sample that we're using for today's little webinar here is totally open source. So I'm going to pull that up in just a moment. But we're going to go ahead and use the build script that's available in this sample to create some new Docker images via Azure pipelines. And then we're going to go ahead and push that Docker image to the Azure Container Registry. This is a private repository of Docker images. One of the best practices I'm going to mention a little bit later is you absolutely, under no circumstances, ever want to push your business's Docker images to DockerHub. You probably will regret doing that. So you always want to have a private repository for your Docker images. And the Azure Container Registry service makes it very easy to get one, and it costs like nothing to go ahead and run one each month. Every time we push a new tagged image to the Azure Container Registry, this is going to trigger the deployment of that Docker image to our Kubernetes cluster via Azure pipelines. And then what's going to eventually happen is all the instances of the service that we're upgrading are all going to be moved from the old version of the Docker image they're running on onto the new version. And that's going to happen somewhat gradually inside the cluster. So I'm going to go ahead and give a demo real briefly. So I'm going to go ahead and pull up my screen here. So I'm going to go ahead and drop a link to this in the webinar real fast. I'm going to go down to chat here, and I'm going to drop a link. So we're going to go ahead and use this Petabridge.Cluster web crawler example. If you want to go ahead and download the source and play with it, it's all right here. And what I'm going to do is I'm going to merge this change from my dev branch to my master branch. So I'm going to do that. You can see this green check mark here. This is the Azure pipelines little build process that I set up. So we run some unit tests, and we go ahead and try a dry run of creating the Docker images under the covers. Okay, Eric, your question. Will we be sharing these slides at the end of the presentation as well? Yes, we will. We'll upload those to SlideShare. Okay, so I'm going to go ahead and fetch the latest images. Let me go ahead and pull up my terminal here. I'm going to go ahead and do git checkout master, fetch Petabridge only. Petabridge master. The reason why I'm starting with the demo first, by the way, is it takes a few minutes for the CI system to go ahead and run everything. So I want to get that going in the background while I introduce you to some of the concepts we're going to be using. So this is the important part right here. I'm going to go ahead and tag this most recent version of the master branch of my GitHub repository as 0.27. That's the new version we're going to roll out. I'm going to go and add a little comment here, 0.27 release. Then I'm going to go ahead and push that, git push Petabridge tags. Now, once this happens, you can see that new tag has been added. If I go to my GitHub repository and I take a look at our releases right here, I can go ahead and see we have this new tag, 0.27. By the time the CI process finishes running, I should go ahead and see cluster.webcrawler version 0.27 with a set of release notes and all of the Git commits that went into this release. That's all going to be populated automatically by Azure pipelines. Okay, so what I'm going to go ahead and do next here is this is my Azure DevOps project for Cluster Web Crawler. This is also public, by the way, so you should be able to see the build progress and everything running. If I go to pipelines, you'll see that I've triggered this release right here for this 0.27 branch. That's the Git tag that I just pushed. And so what's going to occur is if I step into this little rolling build, my build script, which is committed into this repository, is going to be used to go ahead and compile this project. And we'll go ahead and essentially push all of the Docker images that we need to go ahead and I'll basically roll the software out to our Kubernetes cluster. Will all be pushed to the Azure container service down here. So not Azure Container Service, ACR, Azure Container Registry, I believe. So that's going to run in the background for a few minutes. What you'll see here on the Releases tab is we're using Web Crawler, which consists of 4 different services. What's going to end up happening is that we are going to have each one of the different services that Web Crawler uses will be deployed to Kubernetes independently and automatically once that new Docker image hits the Azure Container Registry we're connected to. So if I click the edit button real fast, you'll go ahead and see this gets continuously deployed. And it gets deployed whenever my repository has a new tag that has that version number on it, like version 0.26 or version 0.27. And what's going to occur, if I look at my task definition, and I scroll down a little bit here, I'm going to execute a Kubernetes command that says, I want this stateful set. And by the way, I'm going to explain what all these terms mean. So if you're not totally following, don't worry. We're basically going to change the stateful set to go ahead and change its version of its Docker image to this repository URL. This is the private key for our sort of private Docker image repository. It's going to change the webcrawler.tracker service to use the version number that we pulled from the Azure Container Registry as a result of this release. And we're going to do that for all 4 of the services in our build pipeline. So that's going to take a few minutes. So I'm going to go ahead and let that run in the background while we go ahead and continue through our presentation here. Now, question from Paul. What is wrong with using DockerHub, specifically their private repo feature? Oh, well, there's nothing wrong with using DockerHub's private repos. You just don't want to use the public repository for DockerHub. It's kind of like the difference between publishing your company's source code to NuGet.org versus using like a private MyGet repository. That's what I really meant where I was coming from there. You always want to publish your company's source code to an area you control where the public can't have access to it. All right. Now I've got one more little poll question before we actually really dive into the meat of sort of connecting all these concepts together, which is, have you ever used Akka.Cluster before? So I'm going to go ahead and let that poll run in the background here. This is what an Akka.NET cluster looks like once it's fully formed. Each node on this chart here is its own actor system. And in the context of Kubernetes, each one of these processes here on screen, A, C, D, each one of these would be its own Docker container, is the way we're going to really go and try to deploy this. Now, what's important to take note of here is that every single node in the cluster is connected to every other node in the cluster. This means that one of the things, oh, you can't see the diagram while the poll is on, Did not know that. Thank you, Nelson. Sure, let me go ahead and close the poll real fast then. All right, so in terms of the respondents, 45% have said, nope, never used Akka.Cluster. 12% said yes, just for fun. 21% said yes, proof of concept, and 22% said yes, in production. Okay, thank you for answering that. And thanks for letting me know that the poll hid the slides. Did not know that. All right, so the important thing to note is that each one of the nodes in this cluster has to be connected to every other node. So one of the problems that we have to solve in the context of working with Docker and Akka.Cluster is we need to be able to guarantee that when each one of these nodes starts up, it's able to reach all the other nodes in the cluster, and all the other nodes in the cluster are able to reach it, which means that we need to have some programmatic way of being able to make sure that it can bind to the right IP address. And that's something we're going to solve through the construction of our little Dockerfile. Now, the way an Akka.NET cluster forms, and this is something we teach in a lot of detail in our online Akka.Cluster course, but the gist of it is Akka.Cluster is a peer-to-peer network fundamentally. And so in order to create a peer-to-peer network, we have to have a strategy for allowing the peers to discover each other when they first turn on. And the approach we use for doing that is a fairly common one. It's called a seed node strategy, which means that there's a handful of nodes that are always available on the network at any given time. And we call those seed nodes. So in this case, these two lighthouse nodes running on their own IP addresses are going to be the first nodes we start, and they're going to join each other. What's going to happen in kind of the next pass of forming the cluster is as these other Docker processes start, they're going to go ahead and join both of the seed nodes at the same time. And what's going to happen is these two seed nodes are going to provide information to the web nodes, the tracker nodes, and the crawler nodes about everyone else inside the network with them at the time. And so we're going to use that information to make sure we connect to everybody else. And the cluster is considered to be fully formed when every node who's trying to join has been able to successfully connect to every other node who is either already a member of the cluster or was already trying to join. So this is part of what we need to make sure happens in the design of our Docker containers and the way we're going to set up our Kubernetes deployments in a moment. Now, the reason why this is so important in production is the way state gets distributed in Akka.Cluster, and there's actually multiple ways of doing it. But the way state gets distributed in Akka.Cluster is, let's say node 1 is a node that's connected to a load balancer, and it receives HTTP requests directly from an end user. Well, in order for that node to distribute work to some of the other nodes in your cluster, which maybe do different types of workloads. So for instance, maybe you have an analytics node or a business intelligence node or some other node that has some useful data that the end user needs to either update or get access to. Well, what's going to happen is this clustered router actor that we create is going to add new routees to its routing table as these nodes join the cluster and become available. So this process of being able to make sure all the nodes can see each other and are able to join each other is essential for being able to allow the cluster to operate normally. So you can see here, we're beginning to distribute work to these actors hosted on these other nodes. And then if node 3 joins the cluster in the future, these routers will all dynamically add another route to this node who's now available. And if at some point, let's say the hardware that was running all of our Kubernetes or all of our Docker containers, somewhere else in the network goes down. Well, what will happen is node 1 will be notified that node number 4 is no longer available, and we won't route any traffic towards it. We'll just go ahead and route that traffic towards nodes 2 and node 3 then. So the reason why I bring this up, this is kind of the fundamentals of how Akka.Cluster works and distributes state, but it's all predicated on the ability for that peer-to-peer network to form initially. And that's the thing we need to take responsibility for if we want to do continuous delivery. We need to make sure our Docker containers can programmatically guarantee that every time a new container spins up, it's able to join the others. Every time we remove a container, it's able to leave the cluster gracefully and say that we're not going to be available to do work anymore. And so that's exactly what we're going to show you how to do the next few minutes here. Now, in terms of some other tools for distributing state inside Akka.Cluster, we have tools like distributed publish subscribe. Akka.Cluster sharding. These all work using the exact same mechanisms the clustered router does, meaning they are able to receive those notifications about nodes joining and leaving the cluster. The only difference is that they kind of have a little bit different mode of facilitating that communication across nodes. So this is just kind of a little bit of background on how Akka.Cluster works. And this will help inform us in terms of our design that we're going to use when it comes to working with Akka.net and Docker. So a couple of key terms for Docker. It seemed like most of us were pretty familiar with Docker so far, but for those of you who aren't, I'm going to walk through some of the key ideas real fast. So the first key term you want to bear in mind is an image. The image is essentially like the class definition for a Docker container. It defines all the binary files, the different host features you're going to need. So for instance, if we're using the .NET Core SDK Docker image, that means we have access to the .NET command line interface inside that container. So the image basically defines all those parts that are kind of built together. The next big thing that we need is a repository. A repository is a collection of named and tagged images. So just like how a NuGet package has a name, a NuGet package also has a version specifying which version of the image you're running. That's what the purpose of Docker tags is. And so the way we're rolling out these software updates to Kubernetes is we're essentially telling Kubernetes, use the newest available version of this image. And so that's how we're able to really do this continuous deploy, is Kubernetes is able to swap out some of those containers in exchange for ones that are running a different version of the software than what they had before. We can also do a rollback in Kubernetes, by the way. We can downgrade to an older version of a Docker image if we want. That's really helpful in the event that maybe we discover some regression that we missed during testing. So Kubernetes is really flexible in terms of what it can do. Now, next is the concept of a container. If an image is a class, then a container is an object. This is an instance of an image that's running on a host machine somewhere. And you can have lots of containers running on one host. It kind of depends really on how much work and how many resources a container consumes. And then lastly, we have the host itself. The host is just the computer that's running the Docker engine, and it's hosting, one or more containers at any given time. So hosts can be running Windows or they can be running Linux. It kind of depends. In the Azure, working with Kubernetes, I haven't really seen any Kubernetes clusters in the wild that run Windows containers. I think with Windows 2019 or whatever the next version is, where they're going to have native Linux, the ability to run Linux containers natively, that story might change. So for our purposes today, we're going to be using Ubuntu containers for pretty much everything. All right. Now next, I mentioned DockerHub. You can think of DockerHub like the public images that are hosted on here. This is like the NuGet.org of Docker. This is where all the base images that you're probably going to want to use will come from originally. And like I think like what Paul mentioned is there actually are the ability to host private images on here. So there's a service you can use to host your own private images if you want. You can use that, or you can use maybe the Azure Container Registry, or I think Amazon has and Google both have their own hosted versions of Docker image repositories on their platforms. So there's a lot of choices that are available to you if you want. But this is an important tool to familiarize yourself with. Now, the way Docker gets hosted is the host machine essentially provides a high degree of isolation between all these different containers. However, these containers have the ability to specify at the time they're created which ports can be exposed to the host operating system and which ports will be exposed to each other via the internal Docker virtual network. So we're not going to be using kind of the native Docker networking mechanisms all that much. We're going to let Kubernetes manage that for us in this scenario. But what's important is the ability to go ahead and describe which pieces of network access can be made public and which ones should be kept private. As a general rule of thumb, when working with Akka.Cluster and Akka.Remote, you always want to make sure that those ports, the ones that expose the remoting functionality, should be kept private. The reason is because Akka.Remote is extremely powerful. Therefore, it is extremely dangerous if it's exposed up to the wild. So as you see in our running code sample in a moment here, We are using what's called a load balancer in Kubernetes to go and expose some traffic publicly from some of our Docker containers. But otherwise, 100% of the other networking, including all of the Akka.Cluster communication, is all kept private inside the virtual network that Docker and Kubernetes set up for us. And that's a good practice. The reason for that being that in order for someone to penetrate your network and get access to, let's say, the binaries running inside a Docker container, or to get access to any of the Akka.remote ports, they would need to essentially be able to get access to the host machine that your network's running on and be able to breach through that. And then they need to be able to get through, in the case of Kubernetes, they would need to be able to get access to the role-based authorization system that they have, which, just for the sake of, I'm going to keep it simple, but just for the sake of argument, I have a very difficult time logging into Kubernetes when I have all the permissions sitting in front of me. So trying to do that somewhat maliciously is quite a challenge. So this kind of gives us a fairly robust default security model from day one here. It's not perfect, but it's still a pretty good way to go. Now, this is the really key part of making Akka.Cluster really sing in a continuous deployment environment. This is a process that we refer to as bootstrapping. Where bootstrapping means we're going to go ahead and programmatically give Akka.Cluster and Akka.remote the ability to determine what is the IP address that I should bind to and broadcast to the other nodes in the network, and what port number should I use. And then I also need to figure out what are the seed nodes that I'm going to contact inside the Docker virtual network in order to form the cluster initially. We need to essentially arm our application with the ability to determine these things at runtime without us having to manually provide like configuration updates every time we do a deployment. That would really hinder the ability for Akka.Cluster to do one of the things it does really well, which is scale up and scale down automatically and provide developers with a really high degree of elasticity. That's why it's important to be able to do this programmatically. The last thing we need to be able to do programmatically is guarantee that when an Akka.Cluster node needs to shut down, we need to be able to guarantee that that node can cleanly leave the cluster before the Docker container exits. And so we've actually provided in this code sample and in our little presentation today a formula for doing all of these rather simply. The way we accomplish this is Petabridge has produced a NuGet package called Akka.Bootstrap.Docker. And you can see us invoking it right here. We're taking the HOCON configuration that we shipped with our application, and we have this extension method that the Akka.Bootstrap.Docker package calls, which says bootstrap from Docker. What this is going to do is it's going to inject some runtime environment networking values directly into your configuration prior to starting your actor system. And here's what those values look like at the bottom of the screen. If the cluster IP environment variable is set inside the Docker container, so that's something you can pass into the container when you start it up via, let's say, the Docker command line, or if you pass it in via Docker Compose, or in our case, via Kubernetes. If that IP environment variable is set, that becomes the host name that Akka.remote is going to use. If that environment variable is not available, we're going to go ahead and use the DNS.getHostname instead. Inside the Docker network, every single container gets its own unique host name, so that's actually a safe value to use if you want. Now next, we're going to go ahead and look for the cluster port environment variable. That's going to specify the port number that we're going to use to listen for inbound connection attempts from other Docker containers. And then lastly, we have the cluster seeds environment variable. This is going to be a comma delimited list of addresses that we're going to initially contact elsewhere inside the Docker network. So this is all you really need from a C# standpoint to get your application ready to work with Docker. And here's the good news. If you don't have any of these environment values set, Bootstrap from Docker is not going to fail. It'll fall back and still work locally. So it's safe to use whether you want to run inside Docker or if you want to launch your program from Visual Studio to do testing and debugging, that will still work as well. So you should go and check out the Akka.Bootstrap.Docker package. At the very end of the presentation today, we have a link to all the different open source tools that we're using. So you can go and check that out if you want. Now, the next bit in terms of working with Docker and Akka.Cluster is how we define our Dockerfile. So our application today actually consists of 4 different Docker files, but they all look pretty much identical to this. I think the only thing that's different is the entry points and I believe the cluster port. I think that's the only thing that's different. Otherwise, everything else is the same. So let's go ahead and walk through all the different parts that were used to create this Docker image. The most important part is actually this bit at the top, from Microsoft/.NET 2.1-SDK. This is a Docker image produced by Microsoft, pushed up to DockerHub, that gives us access to the .NET Core 2.1 build environment. That's going to be useful because we actually need to be able to access the .NET tool instruction a little bit later inside this Docker image. So that's why we want to use the .NET SDK. If you don't need access to the SDK, you can use the .NET Core 2.1 runtime image if you want, which is going to be considerably smaller in terms of its file size footprint. So you can do that too if you wish. Then we specify the working directory right here. This basically says, here's the folder that all the binaries that we run inside this container are going to execute out of. Then we're going to specify the environment variables expected by Akka.Bootstrap.Docker. Now, if I didn't explicitly mention these environment variables inside the Docker file, I could still pass them in via something like Docker Compose or Kubernetes. But the reason why I usually do it in the Docker file is I'm kind of letting whoever looks at this code know these are some of the things that we expect. You should make sure you provide these in your Kubernetes file or your Docker Compose file. And I can also specify default values if I want, which I'm doing right here for the cluster port, for instance. So I'm saying we want to default to 5213, which is also the port that we're going to expose to the Akka.remote network down here. We're going to say we want to expose 5213 to the other nodes inside the system. Now, this is the most important step right here. The Docker build process actually runs on like a host machine. So like in our case, with our Azure Pipelines example, it's one of the Azure Pipelines build agent is going to be the one running this command. This command right here is going to tell it, copy the content from the .NET publish command. So, bin released .NET Core 2.1 publish. We're going to go and copy that data into the app folder. And that way we have all the binaries we need to go and run the sample. Now, if you're not familiar with the .NET publish command, what that essentially does is it packages up your .NET Core application for essentially being able to be binary deployed onto some environment somewhere. So everything you could possibly need to run your application all gets copied into this folder. So most Docker images that work with .NET Core tend to use the output from that in order to build it. So that's what we're doing here. Now, next, we're going to be installing Petabridge.Cmd. We're going to be installing the global PBM tool. This is going to give us the ability to allow our cluster nodes to leave the cluster gracefully when Docker attempts to shut them down. So we're going to do that. And then we're going to go ahead and define the entry point for this container. Now, this is pretty important. We're going to say we want to go ahead and run the .NET command, and we're going to pass in the web crawler DLL. This is our sort of program.cs library. We're going to go ahead and run that as the entry point for this container. Now, here's a really important note. If this process dies, let's say the crawler service dies, the Docker container shuts down. So the Docker container's sort of life cycle is coupled very closely to the lifespan of this entry point process. So one of the things you can do that's kind of neat with something like Petabridge.Cmd is if you program your Akka.Cluster application to shut down the process that it's running inside of, if the actor system terminates, in an environment like Kubernetes, that can actually go and trigger an automatic restart of that process if you want. So that's pretty neat. So this is kind of the construction of the Dockerfile. It's pretty simple, and I've gone through and sort of highlighted all the steps here. I'll make these slides available at the end of the presentation. So if you want to go ahead and try basically creating your own Docker files with your own application, you can use this as a template to work from there. Now, one thing I want to mention real quick, if you're not using Petabridge.Cmd, just to give you a little bit of an overview, Petabridge.Cmd kind of consists of 2 different parts. There's a Petabridge.Cmd host that gets installed as a NuGet package, and that runs inside your cluster nodes. And then there's the Petabridge.Cmd command line client. and these talk to each other over a TCP connection. What Petabridge.Command does that's kind of useful is if you go and embed the .NET Core global tool for Petabridge.Command inside your Docker containers, it allows you to do things like manipulate or inspect the shape of the cluster from inside the network if you want. So basically, you become able to go ahead and secure access to the host machine and invoke PBM. So it basically gives you sort of a secure way of being able to manage your cluster without having to expose the Petabridge.Command host to the outside. So let me go ahead and actually say, Paul, you've got a question. Can you copy over to a runtime base image prior to the entry point layer, or does the PBM exe require the SDK at runtime? I think, Paul, you need access to, I think if you go ahead and use the Docker build pipeline to basically say, we're going to build this image up to this point using the .NET 1 SDK, and then you say our runtime image is going to be the .NET 2.1 runtime, that should work, if I'm not mistaken. So that's something that I haven't tested yet, but I think that could work. Now, let me go ahead and give you a little demo here real briefly. So if I go and take a look at our release pipeline, I believe everything should have been deployed successfully. Yep, looks like it was deployed about 20 minutes ago, all of our different little services here. And the way we can tell is this is our web crawler application running on Windows Azure somewhere. And it's running a version 0.26 is what it was running at the start of our presentation. If I go ahead and I reload it, it's now running version 0.27. Awesome. And I'll go ahead and kick off a little query of Petabridge's website here just to see it work. And there we go. Looks like it downloaded all 300 or so of our pages and images in the span of about 10 seconds. Great, perfect. To give you an example of Petabridge.Command working inside our cluster, let me do this. First, I'm going to use the Kubernetes command line real quick. Just a second. So I can see inside Kubernetes, I'm going to explain what all this does in just a moment. I can go ahead and see we've got a number of different pods running 3 crawler nodes, 3 lighthouse nodes, 3 trackers, and 3 web nodes. And then I have some of the networking stuff defined right here. And this is the public IP that we're exposing directly to the external network that users can use to go ahead and submit queries if they want. Now, one of the things I can do with Petabridge.Command is I can go ahead and use the kubectl, which is the Kubernetes command line interface. I can go ahead and use that to execute a command on, let's say, Lighthouse 2. And I'm going to go ahead and say PBM 127.0.0.1. So it's going to connect to itself, cluster show. This is going to go ahead and give me, this is the Petabridge.Command sort of output here, a diagnostic readout of the cluster. That's pretty cool. So let me go ahead and maybe I should try kicking a node out of the cluster. If I go ahead and do cluster leave, that'll cause Lighthouse 2 to execute to leave the cluster on its own. And that'll eventually cause the process to go and shut itself down and get restarted. So you can see Lighthouse node is leaving, it's been removed. And you see we got disconnected here. That's because the container, I believe, is going to be restarted. So I do kubectl get all again. Looks like Lighthouse 2 is currently running. We go ahead and do that one more time. There we go. I can see that the pod Lighthouse 2 has now restarted. And so that's the reason why it did that is because when that node left the cluster, that caused the actor system to terminate. And so the process exited at that point. Kubernetes noticed that and automatically restarted it for us. So that's an example of the type of thing that the Petabridge.Command integration in Docker allows you to do. Not quite done with that piece yet, but we'll revisit it when we actually introduce Kubernetes in a moment. Now, the entire process for publishing a Docker image with .NET Core is usually we begin with a .NET publish command to go ahead and get all the content for our application into a single folder. We then say, okay, we're going to create an image from the Dockerfile we created earlier, and we'll run the Docker build command, and we'll tag that image with a name and a specific tag. At that point, we got to go and push that Docker image to our repository, just like uploading a NuGet package. And we're going to use the Docker push command, and we're going to have logged in to our private repository, and we use the name of our organization, and we'll go ahead and basically push the image name up, and that'll push all the private Docker images up to our repository. Now, in terms of private Docker registries, like I mentioned earlier, you don't want to publish your company's code into DockerHub. And by that, just to clarify for Paul, what I meant was not the public DockerHub. Private DockerHub repositories are just fine. So you always want to go ahead and try to use a private container registry or host service instead. So just to give you an example of what that looks like, I think I have here we go. I have my sort of resource group here in Azure. And you can see I have this container registry off to the right. If I click into here and I click into repositories, you can go ahead and see these are some of the different Docker images that I've been pushing. And if I want to go and take a look at one, let's take a look at web, for instance. You can see that I have a couple different tags. So I've got these few versions of the software going back to 0.23, this 0.27 one that I just created earlier. And then we almost always have a latest version as well. When I do deployments, I always use a specific version number like this, because if I try to tell Docker to say, hey, use the latest version here, well, it might tell me, hey, I'm already using a Docker image with that tag. Therefore, I can't go and roll out an update to it. Whereas if I tell Kubernetes to switch from 0.26 to 0.27, that's a command it understands. That's why we go ahead and we specify that tag filter on Azure pipelines to say, always go ahead and select a Docker image tag that has a version number. So we use a little regular expression to validate that. In fact, just to show that real fast, I'm going to go and edit my pipeline. So I can pull that up, take a look here. This is the filter, this little regular expression I use right here. This lets me look for a version number when I do that deployment. Now, there's other ways you can go ahead and set up from a continuous integration standpoint, this trigger to go and do a deployment. Theoretically, I could have done all this Kubernetes stuff on the back of, if I go to my build pipeline, I could have done it in this step right here, where I'm actually going and creating the Docker images. I could have done it there if I wanted to, but I figured it'd probably be best to have the deployment actually triggered by that new image being pushed. All right. Now, so Kubernetes core concepts. So this is the tool that sounds like most of our attendees today are kind of unfamiliar with. Kubernetes is an orchestration platform. What that means is it networks multiple Docker hosts together into this unified abstraction. So if you want to go and distribute your application's Docker containers over a network of computers, you typically need an orchestration tool for doing that. Kubernetes isn't the only game in town. There's also Docker Swarm, which is actually made by the people who create Docker. There's Apache Mesos, which is another sort of big open source project that has a lot of wide commercial support. Kubernetes is just what we picked because that kind of appears to be the lingua franca of orchestration at this point. Now, the way applications get deployed is we deploy them to the Kubernetes cluster, and the Kubernetes cluster orchestrates the instantiation of those containers across hosts. It's able to do things like guarantee, like, oh, we don't want to make sure if we have 3 web nodes, we don't want to make sure all 3 of our web nodes are all deployed onto the same host computer, because that would be bad from a disaster recovery point of view. So Kubernetes is smart enough to go ahead and start distributing that data across more nodes in the cluster. And you also have the ability, because Kubernetes is highly configurable, to give Kubernetes some hints around how you'd like it deployed. And then that's where the configuration format really comes in. We have the ability to define which parts of our application can be exposed publicly and how. We also have the ability to tell Kubernetes, here's how I want this type of application deployed, and that can be different from this other application that we have. So to go ahead and kind of give you a complete picture of what things look like from a network perspective, this is an example of sort of what our Azure Kubernetes cluster looks like. What we have is we have 3 host machines. In this case, in fact, I can actually show you the Azure output for this in just a second. But we have 3 different host machines that are all running this Kubernetes daemon on it. So if you're interested in looking at using Kubernetes on premise and you want to use a vendor like Rancher Labs or something like that, what they'll have you do is they'll have you go and install the sort of Kubernetes agent on all the different computers that are going to be capable of hosting those containers. And these little agents work together, not unlike what Akka.Cluster does amongst itself, to basically figure out which containers do I have, how much capacity do I have left, and if I receive a deployment instruction, should I try to basically stick that container on here, or maybe is there a less heavily loaded node I can stick that onto? Kind of depends on how you configure things. All of these container instances right here, including the 16666 port on our web nodes, that's all kept private via the Cube network that Kubernetes sets up. It's kind of a virtual network that spans all these hosts. So all these nodes are able to communicate back, and all these containers are able to transparently communicate with containers running on different host machines without you needing to explicitly address that. The Kubernetes infrastructure provides all that functionality to you. And then in cloud platforms like Azure Kubernetes Service, it's really easy for us to go ahead and say, you know what? I would like these web containers to go ahead and expose their port 80 out to an external load balancer that we're going to expose to a public network somewhere out there. So that's an example of sort of being able to have this sort of external ingress routing into your cluster if you want. And the best part is the amount of configuration it takes to set this stuff up is actually not as complicated as you'd expect. So this is sort of what our infrastructure looks like when we've gone and deployed an Azure Kubernetes cluster on AKS. We end up with a network security group, a routing table. By the way, this is all created for you automatically. Like I didn't do any of this. This was all done by, if I go to my Azure UI here, if I go back to my cluster web crawler resource group, when I created this Azure Kubernetes service instance right here, it'll go ahead and basically give me a sense for like the health of the containers and everything else. If I want to turn that functionality on, tells me that I've got 6 cores, 21 gigs of total RAM. Well, all of those actual resources that I'm getting that data from are all these host machines and network interfaces that Kubernetes, that the AKS service creates for me automatically. So this is kind of a good bare metal look at what the actual infrastructure that's running Kubernetes looks like. This is all transparent to me at the time I'm doing deployments or at the time I'm managing my cluster. I don't need to go and worry about any of this on a day-to-day basis. If I want to go ahead and scale up the number of Kubernetes hosts I have, the scale set that's provided down here will be able to help me with that. So Azure does a pretty good job of sort of managing all this for you. If you want to use something like an on-premise host, you'd have to go ahead and set up some of this infrastructure yourself. That's kind of the trade-off, versus having a hosted service versus self-hosting. But the way Kubernetes works is fundamentally the same on both platforms. Now, some key terms for Kubernetes. So, Pankaj, your question. I may have missed this, but how would each cluster in this Kubernetes environment know the lighthouse address, as the lighthouse address would also be dynamic? I'm glad you asked because I'm about to reveal that in a couple moments. So a couple of key terms first before we dive into sort of how we actually use Kubernetes for real under the covers. First is we have a pod. A pod is a single application unit of execution in Kubernetes. Technically, a pod can have multiple Docker containers running inside it. So an example of where you might want to do that is maybe you have your main application running as one Docker container, and maybe you have something like, if you're using Jaeger for doing distributed tracing, you might have a Jaeger agent also running inside that same pod with you, or maybe a New Relic agent or something like that. That would be an example of where having multiple containers inside a single pod makes sense. The next big term we're going to introduce is a stateful set. Now, there's lots of different terms and tools and options and bells and whistles inside Kubernetes, and I can't possibly do all of them justice in the span of an hour. But a stateful set is a type of deployment that we're going to leverage for Akka.Cluster. Akka.Cluster applications are fundamentally stateful, and what a stateful set gives us is a very well-defined way of being able to gently roll out a new version of a stateful service in a way that is minimally disruptive to our cluster. That's really good from an availability and a consistency point of view. So we want to take advantage of that. Then lastly, the other key term we're going to introduce is a service. A service is a definition we provide to Kubernetes that says, here's how I want to expose this deployment to other services inside Kubernetes. Or if I want to expose it publicly, like via a load balancer, that's another thing you would specify in your service definition. So the big thing I want to focus on in the next couple of minutes here is a stateful set. This is really the key feature that Kubernetes makes really easy for Akka.Cluster, is the ability to deploy a stateful application somewhat automatically. So this is our sort of little host diagram from earlier. And let's say I want to go ahead and update my web stateful set to use a different version of a Docker image than what it's currently running right now. So this is the kubectl. That's the sort of command line interface for managing a Kubernetes cluster. This is the command you'd use for basically rolling out an upgrade like that. And that's essentially what Azure Pipelines is doing for me in those release pipelines. So what would happen is in a stateful set deployment, what we do is we swap out nodes one at a time. You have the ability to configure this in your stateful set service definition, so you have the ability to tune it, but this is what happens by default. Is we say, okay, we're going to update container 1 running this old web code first, and we're going to go ahead and upgrade that to run the newest version. Now here's the really cool part. Let's say for whatever reason this deployment fails and the container crashes. Then what's going to happen is Kubernetes is not going to start upgrading the other containers running the service. It's essentially going to stop that deployment. It's kind of like a canary deployment automatically. It's going to say, you know what? We can't get that new node to come online. Therefore, we can't move forward with the rest of this deployment. Someone's got to step in and either roll back to the old version, or we've got to go ahead and maybe cancel that command altogether. So that's something that can and will happen in the event that, let's say, a container doesn't get thoroughly tested enough before it gets rolled out. Kubernetes will help cover your bases there and make sure that you don't end up accidentally nuking your cluster. Now that node's been upgraded, Kubernetes will start work on the next node. So we'll go ahead and terminate that container, and we're going to terminate it gracefully, by the way. So we're going to go ahead and let it gracefully leave the cluster. And then we're going to replace that with the latest code. And Kubernetes will do that until all 6 of these web nodes are completely up to date. So it'll go ahead and run through that process, doing it one at a time. That's much more gentle than sort of the VIP swap techniques and other types of deployments that are typically used in stateless applications. In a stateful environment, this gradual one at a time kind of automated process where each node is given a chance to gracefully exit and then come back online is ultimately much less hard on the system, and gives us a chance to go ahead and persist our data as we're shutting down, gives us a chance to hand over responsibility to other nodes running inside the cluster. All this good stuff that Akka.Cluster likes to do, Kubernetes makes really easy. So that's why the stateful set deployment type is a good fit for Akka.Cluster. There's other deployment types other than stateful sets out there, but they're not really as appropriate as a stateful set is. Now, the methodology that we're going to go ahead and use. All applications are deployed as stateful sets with Akka.Cluster, since state is fundamental to how Akka.Cluster works. All internal Akka.Cluster functionality gets exposed as a cluster IP service. So what this does essentially guarantees that each one of the pods that's running inside Akka.Cluster will go ahead and expose itself to the internal network on whatever its host name is, plus the port number that we assign in our service definition. So basically, this is a way of being able to make sure that all the different pods running on the different host machines have the ability to talk to each other on only the port numbers that we explicitly allow. Next, any public functionality that we want to go ahead and expose to the outside will be exposed as a load balancer service. So we can technically have, by the way, multiple services all talking to the same pod if the pod has multiple IP addresses and ports available, like how our web nodes do. We have both port 80 and port 1666. So if we have that, those will all be exposed. Okay. couple of questions about Kubernetes networking with Akka.Cluster from Daniel. Since Kubernetes will update and replace pods, usually in less than a second, how long does Akka need for that to go down and back up when a node is detected, when a node down is detected during an upgrade? I'll go ahead and show you that, Daniel, in the YAML file that we're going to use to define our Akka.Cluster deployments in a second. We have a way of essentially giving the each node in the cluster a grace period to exit. So that's the way that's something you can specify in our configuration. And then the other question was, what about port conflicts if more than one node is running on, if port conflicts if more than one node is running on the same host? The way we avoid that is the fact that Kubernetes goes and assigns a unique host name for each one of the pods. Therefore, they don't have any conflict. There's some network address translation that happens locally inside each one of the host machines as part of the Kubernetes virtual network. Unfortunately, I do not have enough knowledge about the internals of Kubernetes to go any further down that road, but that's basically the gist of it in terms of why it works. There really shouldn't be any port conflicts, in other words. Kubernetes manages that very carefully for you. And then lastly, to kind of answer Jonathan's the first question that Daniel asked, we're going to use Petabridge.Cmd for node exits. We're going to go ahead and basically make sure each node in the cluster leaves gracefully. And deployments and rollbacks will be performed by simply changing the Docker image tag. So I'm going to go ahead and give you an example of that in just a moment. One question that's been coming up, I've seen a couple of it so far. Would this process be similar to, since we're using Azure Kubernetes service right now, would this process be similar on, let's say, I think the Amazon Kubernetes service? The answer is yes. That's actually identical on both platforms. The only difference is that Amazon requires you to install a little piece of software on the node that's doing the deployment. And that basically allows you to log in using the Amazon Identity and Access Management interface. Once you get that set up, actually the processes are totally identical. In fact, the first time we ran this cluster.web crawler demo for a Petabridge customer, it was actually on Amazon. So you can actually take this, this repository I'm showing you and run it lock, stock, and barrel on top of AWS. Okay, now this is the YAML file that we use for defining a stateful set deployment. And we're going to be deploying our Lighthouse nodes in this instance. So the first thing we do is we go ahead and declare this is a stateful set. This is going to tell Kubernetes, how do I want to roll this out? Next thing we're going to do is we're going to say, okay, the name of the service that basically is going to be pointing at this specific deployment here is going to be Lighthouse. So that's our service name. That's going to be useful later. We need to go ahead and define basically how to have Kubernetes go and point its cluster IP at us. And then this replicas 3 number is going to say, we're going to initially begin with 3 pods all running at the same time. And then this match selector is basically a way that other services can go and refer to us. That's kind of what that's for. Now, this is to answer Daniel's question from earlier. See this spec right here, termination grace period seconds 35. What this means is we're essentially telling Kubernetes, give this node at least 35 seconds, or give this node exactly 35 seconds to try to shut down. If it shuts down sooner than that, great, swell, that's awesome. But essentially what we're doing is we're able to spread out how quickly the rollout happens that way. If you need a longer grace period, you can go ahead and widen this out, and that'll go ahead and give each pod in the cluster a little bit of time to restart when you're doing a new deployment. And then down here in the spec, we specify all the different Docker containers that are going to be running inside this pod. So in our example, we're only running 1 container inside each pod. And we're going to go ahead and say, okay, this container is going to be called Lighthouse. This is the Docker image we're going to use. If we're going to use, by the way, let's say a private image repository, we would probably want to have the URL of that private repository here in front of the Docker image. And then we specify the tag that we're going to use. Now, this is the really important bit down here, this lifecycle pre-stop. What we're doing here is we're telling Petabridge.Cmd that basically before we terminate this pod, in the event of a shutdown, or if we're scaling down the cluster, or if we're going to roll out an update, we need to go ahead and execute this command inside the Docker container. PBM 127 9110. This is the default address the Petabridge.Command host listens on. And we're going to say cluster leave. That's going to cause this process to terminate by having it exit the cluster gracefully. And that's why we have this 35-second grace period up here. Gives us the ability to go ahead and swap out these nodes in the cluster gracefully. Now, the last bit of this sort of YAML file here, and this is to answer Pankaj's question from earlier. This is where we define our environment variables. So one of the things I'm going to do is I'm going to create an environment variable called pod name. And I'm going to go ahead and extract from the metadata that's being used by the Kubernetes engine when we're deploying. I'm going to say we're going to populate this pod name variable with the name of the pod that we're instantiating. And then down here, I'm going to go ahead and customize the IP address that we're going to be bound to using that pod name environment variable. And then I'm going to prefix it with Lighthouse at the end. And then Pankaj, this is where we go and we specify the seed node configuration on all of our nodes. We're going to go ahead and say, since we're expecting at least 3 Lighthouse nodes, we're going to go ahead and say, okay, here's the full Akka.TCP address that we're going to pass in as an environment variable to our Docker container. And so we're going to say, okay, it's lighthouse 0.lighthouse on port 4053. And we're going to go ahead and repeat this for Lighthouse 1 and Lighthouse 2. And then at the very bottom, we have this liveness probe. If Akka.remote shuts down, this is the Akka.remote port we're listening on. If Akka.remote shuts down for any reason, this liveness probe will fail, and that'll cause Kubernetes to go and restart this node in the event that it wasn't a planned shutdown. So when I called cluster.leave earlier, without trying to manipulate the pod, that liveness probe is what failed and what caused Kubernetes to restart that container. And then finally, we go ahead and we define, here's the port that this container can expose to the internal Kubernetes network. All right, question from Rob. Could you give a bit more information on why Akka.Cluster needs a stateful set than another type? What state does it need to keep that isn't just application defined? Or is that just due to the start-stop ordering, graceful stop? Okay, Rob, 2 reasons. The graceful stop is important for Akka.Cluster. But the other state that Akka.Cluster nodes typically have is actually the connectivity and membership state. Since Akka.Cluster is a peer-to-peer network, every single node in the network needs to have a copy of what the sort of current view of the cluster's membership looks like. Being able to allow these nodes to leave gracefully and rejoin basically makes sure the cluster is minimally disruptive. On top of that, we also want to guarantee that at any given time inside the cluster, that there's at least one node of a certain role type available. The stateful set deployment technique essentially guarantees that's going to be true, because rather than replacing all the nodes at once, which might be disruptive, we are basically able to guarantee that they sort of swap out one at a time. So it kind of gives us a more graceful sort of way of being able to swap out the cluster's membership out from underneath it. Now, the last little bit from a YAML point of view is the service definition. This is pretty straightforward. So we basically go ahead and we pass this in. We say this is the service. We're going to be targeting the Lighthouse application, and we're going to go ahead and expose this port 4053 out to the rest of the cluster somewhere. And when I say the cluster, in this case, I mean the Kubernetes cluster. This is going to tell us that, okay, we want to expose port 4053 out to all of the other services that are running inside Kubernetes. And we want to do it on this port number. And we're not going to specify an IP address here. We're going to let just the host names that are assigned by Kubernetes do it. And so just to show you sort of what the complete file looks like. So I'll pull up my YAML file here. This is inside the open source project. Typically, when I go ahead and I set up a Kubernetes deployment, I go ahead and I have my service definition at the top. And then I have my sort of stateful set definition down below. And if you see something that's a little bit more sophisticated, like let's say our web service. So our web service is going to go ahead and basically expose, its clustering port on port 1666. Then on top of that, if I scroll down, we also expose port 80 down here. And what I'm going to do is I'm going to go ahead and create another service, this web cluster HTTP service, as a type of load balancer. And I'm going to say we're going to use a protocol of TCP, and we're going to go ahead and target port 80 for that. In the Azure Kubernetes service, when I go ahead and execute a deployment like this, it's going to go ahead and create a software load balancer that's going to basically just expose that traffic on a public IP address that gets assigned automatically by Windows Azure. There are ways you can specify a static IP address for doing that if you want, but that basically just kind of depends a little bit on how you configure things. That's a little bit beyond the scope of what we're going to cover today. To actually go and create these services for the very first time, you want to use the kubectl apply command. So before you start doing continuous integration with Kubernetes, usually you want to walk through and do this first to create your initial set of services. So when you call kubectl apply and you pass in that YAML file we created, that'll tell Kubernetes to start pulling down all the different Docker images you needed. It'll set up the pods and distribute them across the host machines, and it'll set up any of the services that you might need. So rinse and repeat for every single service inside your cluster. Now, from an Akka.Cluster standpoint, I try to basically create one Kubernetes deployment for each service type. And so the services that are running inside Kubernetes align very closely to the roles I'm using inside Akka.Cluster. And one thing I will typically try to do, although I'm not doing it very well in this code sample, one thing I'll typically try to do is I try to make sure that I only update one service at a time. So in order for you to do that in a real world scenario, you'd want to have your services running in like separate, GitHub repositories with separate, deploy hooks and all that stuff. But because this is a example application for learning, we combined it all together. The reason why you want to do that is usually you'll have the best results in your cluster if you're not trying to update everything at once. So that's why I typically recommend that people should try to deploy things only when they need to, and they should do it individually. Now, just to give you a little example here, if I go back to our crawler, so we're running version 0.27 right now. It looks like someone kicked off a crawl in the background, and we've downloaded, let's say, 9 gigs of data. That's pretty cool. That's, I guess, the danger of exposing this publicly on the open internet. So one thing I'm going to go ahead and do real fast is I'm going to go ahead and pull up kubectl exec, and I'm going to go ahead and run this on Lighthouse 1, PBM 127.0.0.1, cluster tail. What the cluster tail commands allow me to do is let me see changes to the cluster be made from an Akka.NET point of view in real time. So I'm going to go ahead and go to Kubernetes here, or should go to Azure Pipelines, and I'm going to manually kick off a release. I'm going to go ahead and disrupt this job that's in progress here. And see, you know what? I'll go back to here. I'm going to go ahead and do create release. We're going to go ahead and do deploy to Kubernetes. And let's see, the artifact, I'm going to go ahead and do 0.25. I think we're running 0.26 right now. Manually go and create that. And I click into this here. So this is a manual release. So I'm going to go ahead and take a look at this manual trigger. Options, deploy to Kubernetes. It's not letting me do that right now, so I'll go ahead and take a look at the old view. And let's see, I'll go ahead and run that deployment. Okay, so this is going to start kicking off a release. If I go back to the pipeline view. All right, so that task is now in progress. So this is what happens automatically typically when I go ahead and update a new Docker image, although I just kicked it off manually here. It looks like kubectl is doing its deployment. I'm going to pull this up. All right, looks like the deployment succeeded. What we should see in any minute here, there we go. We can see nodes beginning to leave the cluster. That's good. More nodes, see that member's been removed. We should see a tracker 2 should rejoin the cluster in a minute once it gets restarted with the latest version. There we go. We see tracker 2 is rejoined the cluster. And this is Kubernetes essentially. This is Kubernetes basically just swapping out these nodes one at a time. So I go to kubectl, you get all down here. And I pull up the screen. We can see that tracker 0 is terminating, and that these other two nodes have already been updated. If I do this one more time, go ahead and pull that up. You see that all of the nodes, all of our tracker nodes have all been upgraded. And this is because that node basically was able to leave the cluster relatively quickly. If that node was running something like Akka.Cluster sharding, it would have taken it longer to leave. So a couple of final notes here since we're running a little long. So the Azure Kubernetes service, which I mentioned earlier, it's managed Kubernetes on top of Azure virtual machine instances and other resources. It's easy to set up and instrument. And really, it's the fact that the Azure CLI makes it really easy for you to do things like automatically authenticate with Kubernetes. It works really well with Azure DevOps. And the Azure Kubernetes service has this unique feature called dev spaces that makes it really easy for, let's say, if you have a team of 20 developers, each developer can have its own development space inside the Kubernetes cluster. They can set up their own containers and everything else without having to trip over anyone else. So dev spaces kind of makes it possible to do, let's say, multi-tenant sort of partitioning of a Kubernetes cluster within your local development team. So, and let's see, Gregorius, your question: do you have an Azure Kubernetes tutorial recommendation for people who've never used Kubernetes in Azure before? Why, yes, I do. If I go to the very end here, oops, sorry about that. I have a list of links that we're going to distribute. The one I really recommend, Gregorius, is this AKS walkthrough down here. Sorry. This AKS walkthrough down here, and don't worry, I'll distribute these slides at the very end. That's a really great tutorial. I think you need to sign up for an Azure account first, but otherwise, once you've taken care of that, this kind of gives you some step-by-step instructions for how to do it. And there's also lots of tutorials on how to do things like set up Azure pipelines to integrate with it. And there's also some content around being able to do things like create custom repository images and all that other good stuff. So, all right. And then the last thing I want to mention before I answer the rest of the questions here is if you're really interested in getting some hands-on training with Akka.Cluster and Kubernetes, I'd strongly recommend taking a look at our training tour. This is the URL for it, and I'll drop that in chat. We just announced today that we're going to be doing a training tour in Amsterdam in August. So we're doing one here in the United States. This is a 2-day-long workshop where we're going to go ahead and cover end-to-end all the different bits you need to do to basically build applications with Akka.Cluster, .NET Core, Docker, and Kubernetes. We're doing one here in Houston on May 30th and 31st, and another one on Amsterdam on August 15th and 16th. And we just started selling tickets for these today. If you're interested in learning a lot more and getting some hands-on practice with it, I definitely recommend signing up for this, and we'll be sending some emails about it. But otherwise, thank you very much for attending today, and I'd be happy to answer some questions before we go. All right, so let me take a look at sort of the top of my list here. Okay, answer that one, answer that one. Okay, Russell, I think I answered this earlier, but I'll go ahead and cover it again. Would it be more or less the same to use the AWS Managed Kubernetes Service, EKS, compared to Azure? Yes, they're very similar. So you'll have a very similar experience with each. My personal experience, having used both of them, is that I think the Azure service is a little bit more polished in terms of getting that stuff set up. There's a little bit of kind of kludging together you have to do. That being said, I'll see if I can find a link to it. There is a very good step-by-step bootcamp tutorial that the Amazon team put on for how to do everything with EKS. And I follow that myself, so I'd strongly recommend it. I'll see if I can dig up the link for that. How to update cluster singletons. Boris, I've got some great news. This process I just walked through actually handles all of that automatically. As soon as a node gracefully leaves the cluster singleton can move from point A to point B. So this whole process I've designed is designed to basically make sure that tools like Akka.Cluster sharding and cluster singletons can move easily and frictionlessly throughout the cluster. Let's see, and I'll get the folks with their hands raised in just a second too. For Akka.NET and Akka.Clusters, is there any performance benefit to use Google Protocol buffs rather than Message Pack? Honestly, both of those really fast. I don't know which one would necessarily be faster. We use Protobuf ourselves at Petabridge and inside the Akka.NET project, but Message Pack is a popular choice among some of our users too. Let's see. Next question. Would there be any issues setting up an Akka.NET cluster within a managed virtual private cloud, AWS VPC, Azure Virtual Network with access through a VPN? Not as far as I know. We've run Akka.NET clusters inside virtual private clouds on Amazon before. As long as basically the nodes are reachable, everything should work. Let's see. Let's see. Let's see, a question from Jonathan. Do you have a recommendation for the Azure VM size to use for a K8s node that will allow us to optimize thread and CPU usage efficiently? Do you suggest a smaller collection of large resource machines or a larger collection of small resource machines? I ask that because at the moment, AKS makes it a pain to change the VM size of the nodes. Yes, it does. And you have to recreate the cluster, and we want to try to avoid too many cluster recreations. John, my recommendation would be, I think, depending on how your application runs, you might be better off running with a smaller number of bigger machines initially. The reason being that is if you have an application that scales vertically, meaning let's say it uses a lot of RAM to do like a lot of computation in memory, it's much easier to deal with that type of problem by basically running on a big machine initially than it is to try to distribute that work across a much smaller number of computers later. So I'd probably recommend setting it up that way. That being said, in either one of those cases, if you start off with bigger machines and you need to add more big machines later, that's perfectly fine. The one issue you could run into with having a smaller number of big machines, of course, is that if one machine goes down or gets upgraded, that affects a larger part of your cluster at any given time. But that's worth the risk, I think. Let's see, Ned. Is it possible to integrate IIS with Kubernetes and Akka.Cluster? Given that Kubernetes has very limited support for Windows, I don't think so. Or at the very least, it'd be very difficult. What you'd be probably better off doing is you'd probably be better off hosting your IIS applications separately and having them network with the Kubernetes nodes via something like an exposed endpoint somewhere. Essentially, what I would do is I'd partition the IIS stuff out of the Kubernetes cluster, and maybe have it communicate through Kafka or something like that, or RabbitMQ to the Akka.Cluster. That'd probably be the way I would try to do that. Let's see. Eric, does the cluster have a shared user session state across all containers? Typically, no, it doesn't. What Akka.Cluster has is it has membership state, which indicates who are the current nodes that are participating in the cluster still, and there's a full copy of that on every node. But other than that, the cluster is totally unaware of everything your users are doing unless you explicitly tell it to be aware of it via the code you write. Jonathan, have you made use of dev spaces with Akka? I have personally not tried it yet. It was a cool feature that I found out about while I was playing around with it. It looks promising. I'll let you know when I have a chance to work with it. Let's see, is it possible to run Akka.Cluster on Amazon ECS instead of Kubernetes? So Azure Container Services and Amazon Elastic Container Service are both essentially being deprecated in favor of their managed Kubernetes options. The reason is because essentially the Kubernetes orchestration sort of methodology is kind of a solved problem that those companies, Amazon and Microsoft in this case, can both leverage rather than trying to have it to do it themselves. So they're trying to steer their customers away from it. That being said, I'm certain it is possible to run Akka.Cluster on ECS, but you probably wouldn't want to, given the direction the platform's moving in. Gregorius, for staging and or testing, would you recommend hosting it locally or making a new Azure Kubernetes cluster? That's a really great question. Some of the managed Kubernetes offerings like Rancher Labs have the ability to do light dark deployments, where you basically have a dark version of your application that's running all of the latest code and is actually running all of the production traffic. Essentially, it does mirroring of production traffic from the production end to the sort of dark end, and you can swap those out at runtime if you want. That's really cool. That's kind of part of what their proprietary offering does. What I would probably do instead myself, I'd probably maintain a separate Kubernetes cluster for staging and testing, and then another one for production. And rather than trying to do a live VIP swap or anything like that, I would probably just go ahead and do what I've been doing here, where you roll out the containers one at a time. Okay, let's take a look at some of the folks who've had their hands raised. So I'm going to go ahead and go to the list here. Let's see, Boris, did I answer your question? Let me unmute you real fast.
Yeah, my question was about the processing.
Okay, good. Glad I could help. Okay, let's see. I think that's it as far as hand raises. One last question. Jonathan, have you seen anyone trying to use Akka and Kubernetes across different regions, which will then be separate VNets and then join via peering and or VPN? This is to try to make it higher availability. Probably more of a Kubernetes question. That's definitely more of a Kubernetes question, Jonathan. I'd love to try to answer it for you, but I'm frankly not that deep on my sort of Kubernetes networking knowledge at the moment. Here's my guess. As long as you can make the virtual network addressable across both data centers, Akka.Cluster would have no problem with it. And this technique with basically really the heavy lifting in this demo today was all really done via the way we define the Docker containers primarily. So this technique would still work in that environment. I'm very confident of that. The only thing that would basically really be that you kind of have to figure out is really how to set up your Kubernetes cluster in order to do that initially. Okay. Well, everyone, thank you very much for attending today. I hope you found this helpful. We're going to be publishing some more content out to our website over the course of this year, particularly as we do these training tours later this year on Akka.Cluster and Kubernetes. Our goal is to try to make it a lot easier for our developers to get up and running with Akka.Cluster in these environments. So thank you very much for your time today. Oh, one more question. We have Akka remote nodes on Windows containers due to legacy requirements. Do you ever see any problems with moving that to Akka.Cluster? When Windows Server 2019 comes out, which has native Linux support, it should be really easy to drop that into an Akka.net, to a Kubernetes cluster. I think there is some support for being able to have there's some support out there. I've read some of it on the Kubernetes website for being able to support Windows containers. It's just not really easily supported right now. And I think if anyone's going to figure it out, it'd probably be the Azure team on AKS. They'd probably be the ones that get that right. Okay. Well, thank you very much for your time today. We'll be emailing out the recording automatically a little bit later today, and we'll also be putting it up on our YouTube channel. We'll probably also be sending everyone a survey who attended today. Would love to know how well we did, but thank you very much for your time and for your support. Thanks again.